way we did that is we actually built a joint probability distribution. So I forgot to put the microphone on. We actually built a joint probability distribution over the inputs and the labels. So P of X, comma Y. That's hard to do in general, so we actually did is made factorization assumptions. So we assumed, first of all, the normal assumption that the data was, each data point was independently sampled, independent identically distributed, given the parameters of the model. And then we made a further assumption. That assumption was enough to start talking about Bayes classifiers, but the further assumption we then made for the class conditional density distributions, that's the distribution over the features given the class, was a factorized independence assumption over the features. And that's known as naive Bayes, the naive Bayes classifier. This week we're going to do something different, and it maps back a little bit more to what we were doing with regression. In fact, the first thing we'll look at is called logistic regression, which is we're going to do classification by directly modeling P of Y given X. So last week, in effect, you won't always see it introduced like this, but what you effectively do in naive Bayes is you define a joint distribution over your entire vector of labels Y and your entire matrix of features X. And then you use Bayes' rule to compute the probability you're interested in, which is P of Yi for a given class, or let's say Y star for a test class given X star, comma X, comma Y. That's the thing you're really interested in. This week we're going to revert to the thing we're doing with regression, where we just model this directly, where we model the relationship between one feature vector and a target vector Y. But in this particular case, instead of what we've been doing before is where Y is Gaussian, now Y is going to be a binary variable, a class label. Okay, so that's probably what this is. Only there's a spelling error there. Distribution. So now we're doing direct estimation of class membership. Now the advantage of doing this is we don't have to make such strong assumptions about the data generation because we're modeling this directly. In order to do the naive Bayes, we had to make very strong assumptions about how this joint distribution was declared, because you can't actually just fit this in general without specifying some assumptions about how data interrelates. Now, those assumptions turn out to be very strong in order to do naive Bayes. They're a lot weaker, I think. They're not easy to directly map the equivalence of the assumptions, but I think they're a lot weaker assumptions when you do this. So we'll do that, and then right at the end, I'm going to use that as a motivation for introducing a framework of models called generalized linear models. So generalized linear models is, so we've seen regression so far. That's a linear model. It can be nonlinear, remember, in the prediction function, but it's talked about as a linear model because it's linear in parameters. So generalized linear models allow us to sort of use linear in the parameter models to make predictions over discrete labels, counts, various other things. It's an entire framework of modeling. We'll have like 3 slides on it. You could do an entire course on generalized linear models on its own. But it's nice to sort of just show you that, having introduced logistic regression. So the advantage of modeling the entire density as we did for naive Bayes is that allows any question about your data set to be answered. You can formulate any question. Given this label and this partial set of features, what should the other features likely to be? What's their distribution? In theory, you can do that. Of course, in practice, you've made such simplifying assumptions that those answers are likely to be poor. So that's the strong assumptions on your data generation distribution are a problem. So in regression, we're modeling this probability of Y given X directly. Now, it allows less flexibility in the question. For example, it's quite hard now to deal with missing data in this case. You haven't made assumptions about the generating distribution for X, so if X is missing, since you're conditioned on X, then you have to do some sort of point imputation. You have to make up values for X. You have to do a separate stage for that. And that's done quite a lot, actually, in these regression models. And actually doing it that way around is sometimes better than trying to deal with missing data in a naive Bayes framework. but it gives you much more flexibility in the model assumptions. And you don't have to just do this for regression, you do it for classification. And as I said, the framework is known as generalized linear models. So the thing about doing this is so far we've been dealing with numbers on the real line. So we've been talking about things as typically we've said we've got a function of x which is equal to w transpose phi of x, right? And that gives us a nonlinear function of x. Linear in the parameters, but the basis functions make it nonlinear in x. Now, that, of course, unless we start putting constraints on the form of phi and w, that maps to the real line. So the domain of this function is the codomain of this function is the real line. What we want to do here is not map to the real line, but we're interested in the probability of a positive outcome or the probability of negative outcome. Remember, we looked at the Bernoulli distribution last time, and the Bernoulli distribution was parameterized by a probability of positive outcome. We'll look at the Bernoulli distribution again in a moment. And what we do, instead of modeling, well, the sort of generalized linear models perspective of this sort of thing says, well, okay, this maps to the real line, but we're interested in a probability. But what we'll do is we're going to take that probability and we're going to do two steps. First of all, we're going to look at the odds ratio. So the odds ratio is the ratio of positive to negative. Okay? It uniquely determines pi, although it involves pi twice. There's a unique mapping between odds and the probability. And in fact, this is how bookmakers will quote probabilities. Of course, in bookmakers' case, so people know what bookmakers are for, if we sort of say the probability of, we could say the probability of Donald Trump being president would be 1,000 to 1. Even that's quite horrifying. But that would be, that wouldn't be a probability, that would be the odds. So it would be 1,000 to 1. So that would be actually 1 in 1,000. So the ratio between these two is 1 in 1,000. It's a way of expressing probability, and bookmakers do it. So that's known as the odds, the probability of positive outcome. So positive outcome is he's not president, I suppose. And negative outcome is he is president, let's just say for the sake of argument. And that would be the ratio between the two. Now, if you take a sort of number between 0 and 1 and you put a ratio in this way, you actually map it to be a number between 0 and infinity. So because the odds can be 1 in 1,000 or 1,000 to 1, right? So 1,000 to 1 is 1,000. 1 in 1,000 is 0.01, sorry. Yeah? So that's, the odds themselves are actually numbers across the entire real line. Now what we then do is, that's positive, the odds themselves are numbers across the positive real line. Now what we then do is we take the logarithm of those odds. Once we take the logarithm, that maps those 0 to infinity to minus infinity to infinity. And then what we say is we're modeling the log odds with this. So this thing has this codomain of minus infinity to infinity. And if we say that the result of that is the logarithm of the odds, then this gives us a way of building the linear model. Does that make sense? We'll look at another way of thinking it in a second, but that's the way it's introduced in statistics. So what people basically say in statistics is they say, well, log of pi of x over 1 minus pi of x is equal to w transpose phi of x. And that's the way you write this down in a generalized linear model. This function here that has this operation on pi is known as the logit function. And it's called, in this general framework, it's called the link function. Because it somehow links the linear model. It links your model to something where things are additive. I actually think it's not a very intuitive way of doing things in some sense. The nice thing about it is what you get to do is you write down your model like you were writing your regression model. The thing on the right always looks like your regression model. You get some sum of terms. And in statistics, that's really important because often those terms have meaning. You're often adding different components together. You're sort of saying, oh, one component, I'll use an example with a Poisson distribution later. One component is space and one component is time, and they're additive in some way. They're log additive in that case. So, this is what I just sort of written down there. So, I've written this as an inverse, actually. So I'm calling this is the link function, and I'm denoting the link function as G inverse. So obviously that's because I'm going to invert it soon. And that's the sort of framework in generalized linear models. And for logistic regression, and the logistic is actually referring indirectly to this logit function, we have this sort of form. So we're taking the logarithm of the odds of the positive probability of positive outcome to the probability of negative outcome, the ratio, is given by this sort of linear function here. Any questions on that? Is that clear? So it's a way of sort of, we are interested in the probability of positive class, but we have to do some sort of weird mapping. And that's the way they sort of did it in statistics. So actually in machine learning, I don't know to what extent it was an independent arrival at the same idea. It doesn't really matter. Conceptually, when people wanted to do the same thing in machine learning, they did something rather different. They did it with neural networks, actually. And they actually wrote it down in this terms, which is actually quite a lot easier to think about in some respects. So this is the sort of generalized linear model formalism, and this is called the link function. In machine learning, we often think of the inverse link function. So I've called that G. In fact, I would think of that as a transformation function, or sometimes we'd call it a squashing function for reasons we'll see in a moment. So what we're really saying is pi, it should be pi of x here, I suppose. Pi as a function of x is equal to, obviously, the relationship above, the way I've set that up is, in order to write this thing below down, I simply have to invert the function on both sides, apply the inverse function to both sides, and then this relationship becomes true. So I should have had the, that's maybe why I didn't do it. So I'm applying the inverse of the link function to both sides, and that gives me this relationship. Now, that relationship can be much more natural because in some sense that's the way your data is being generated, what your claim is in your model. This is also the prediction function. Yeah? So this relationship is the sort of thing you'll see in machine learning, but this is the formalism you'll see in texts on generalized linear models. They like to have this. This is an additive term, right? So it's really the sum of W1 times phi1 plus W2 times phi2. So you've got an addition on the right. That emphasizes the linear nature of the model, yeah? And then you've got the link function on the left, which is, so it's why it's generalized linear model is not fully linear anymore, right? Because there's a non-linearity. But the form of this non-linearity is very specific. It can be written in this way. Yeah? Does that make sense? But this is the way we might think about it in machine learning. And I think in some sense that's an easier way to think about it. Because that inverse function has this shape. And we'll see the formula for it in a moment. But it's sometimes called the squashing or the sigmoid function. So I should have made this line thicker, shouldn't I? But this is, if this is the input coming in, this is what G says on the output. So this is f coming off from our basis function model. So that can be anywhere on the real line. But whatever f comes in at, and this function has a minimum at 0 at -infinity. It's got a maximum at 1 at infinity. So it's always between 0 and 1. So whatever your value comes in out of your model, so like imagine what's going on in a regression model. You normally are predicting, you know, some 4 minutes per kilometer or something. Well, but that's not the thing you use. That comes out here, and then that gives you something which can now be treated as a probability because it's between 0 and 1. So this GI is, of course, pi in this case. You can see why we might call that a squashing function. So you'll hear that term used in machine learning as well. That you've got some sort of number which is in the real line, and you want to squash it to be across 0 to 1. But it's not actually the link function. This is often a confusion. The link function is the inverse of that. But it is the way that we would naturally think about the data being generated. So we think we've got some input data in the prediction function. It goes through this sort of basis set, comes into this real line, and then comes out as a probability. Yeah? So this is the formula for that inverse function. So inverting, so before we had a function effectively saying that this was equal to something that was a function of pi, the G inverse. This is the function G. So it's very simple. It's 1 over 1 plus e to the, this is f of x here, right? So this would be f of x always. But in this case, we've substituted in the basis function. So the nice thing about this, everything I've taught you so far, so logistic regression, you might just use, of course, you would know that, of course, doing that is valid as well. That would be a classical logistic regression where you're just taking some features. If you want to do nonlinear classification, though, we just introduce that. Yeah, we just introduce the basis functions. So the initial linear classification model is actually obtained by doing that. But you've already seen how basis functions are introduced and so on and so forth. And by introducing basis functions, we make everything nonlinear. So I'm not even going to sort of go through the specifics of that. That's already been done. You've got a basis set. You're doing the classification on the basis set. So you get a nonlinear function of your inputs rather than the linear function of the inputs. Make sense? So once we've got this, we use this value of the prediction function in a Bernoulli distribution to form our likelihood. So just as a little reminder of the Bernoulli distribution from last time. So the Bernoulli distribution was just a mathematical trick for giving us different probabilities according to y. So if y is 1, y is, remember, binary in this case. That's the actual observed label. Pi is going to be our sort of prediction from the model. If y is 1, then it just selects pi I. If y is 0, it selects 1 minus pi I. So we're getting the prediction out of the model, which is going to be in the form of this prediction function we've just seen in the previous slide. And then in the likelihood, yeah, that gets inserted into the likelihood, and then from that we'll form our objective. So it's just like regression in that we have a prediction function, we have a likelihood function, and that gives us an objective function. I mean, the reason for teaching you things in this way is because, you know, that's the standard approach to building probabilistic models. But always a prediction function. We saw that in latent variable models, right? In latent variable models, the prediction function was somewhat hidden because we had to integrate over its inputs. So, you know, maybe there's not necessarily a prediction function there. But whenever we're doing these regression cases, we're building these prediction functions, and then we're constructing a likelihood around it, and then we're getting a negative log likelihood. That gives you the framework to go beyond. Now, you see, if you want to do some other type of data, you know the theory of how you build up the model, and we'll briefly review that with the Poisson at the end. So in some sense, yeah, I always think of this as actually just a... I mean, that requires more text, but somehow that's a more intuitive way of writing that. Or even writing as a table would be a classical way of representing it. But it's a nice mathematical representation. So in maximum likelihood, we're just going to do the same thing we've done every other time for this, apart from in the Bayesian case. But even in the Bayesian case, we assumed this, and then we had a prior over W, which we integrated out. Conditional independence of data. I always emphasize that because it's not saying that the data is fully independent. It's conditionally independent given W. It's only independent if you know W, right? If the data was really totally independent from each other, then there would be no point in doing any learning. There would be no relationship between the data. So it's conditionally independent given W. So that gives us a log likelihood of this form. So taking the log of the Bernoulli, which we also did last time for doing maximum likelihood in that model, gives us the yi pops down from the top of the pi I, and we get a yi log pi I, and then we get the same thing for the second term because they're just in a product. And because of the sum outside the whole thing, we've got a sum outside on both terms. Now, having said that, all we need to do is substitute in the form of our prediction function for pi I, yeah? So the probability of a positive outcome for the ith data point is simply this. It's the squashing function applied to the W transpose phi from before. And so that can just pop inside our prediction function. So compare this to the Gaussian case, where in regression, we were writing down the likelihood in terms of the mean and the variance. And then we replaced the mean with the prediction function. And that was fine because the mean is infinity, minus infinity to infinity, are valid values for the mean. In this case, pi has to be between 0 and 1 because it's a probability It's effectively normalized by forcing 1 minus pi on the other side, right? So we don't really have to worry about the normalization in this case. It's a discrete probability. So we just substitute with the squashing function. And that's sort of how a machine learner would typically view what you're doing here. A probabilistic machine learner would view it. They wouldn't view it in terms of the link function perspective I introduced earlier. But they're just two sides of the same coin. The link function is the inverse of this squashing transformation. Now, the slightly irritating thing is this gradient is, so what we need is the gradient with respect to parameters, as before. So the gradient with respect to parameters, this is just a function of w, this is just a function of w. Just looking at this, it's a nested function. So we need multiple applications of the chain rule, right? So this log is got to be the derivative of the log multiplied by the derivative of g multiplied by the derivative of this. What is the derivative of that with respect to w? Of this thing here with respect to w? Phi, yeah, precisely, phi. So the derivative of this inner thing is phi. So phi is the sort of thing that you first care about. Now you need the derivative, multiply by the derivative of that, and multiply the derivative of that. So when you do all those steps, above and below it's the same thing, it's just the function's slightly different. The derivative of log is 1 over the argument of the log. Yeah? There's a yi as well there as well. 1 over the argument of the log. The derivative of g I've just written as the derivative of g. Yeah? And then phi is the derivative of w. So that's just the chain rule being applied in a multivariate way. Same thing here, only we get a change in sign. It's negative log likelihood, so there's a negative on this one here, but this one, there's a minus in front of the g, so you get a change in sign here. So this term here looks similar. All the terms are the same in terms of it, but with 1 minus in here. So for any given data point, you can actually see what the derivative of is for an individual data point. Because what we're going to suggest in a bit is this gives you the actual full gradient. But what did we do in like early lectures? Do you remember the objective function for matrix factorization? What approach were we using there to deal with very large data? People remember? Let's give us the batch gradient. Yeah, stochastic gradient descent. So what you'll very often see is update algorithms that are based on one data point of this. That's the stochastic gradient descent algorithm. So just observing a data point, computing the gradient with respect to that data point, and then making an update. In that case, if the gradient is, if the data, that label on that data point is positive, well, this term zeroes out, and you only get this term. So looking at the gradient with respect to one data point, you've got a sort of 1 over the current probability of that data point being true. Now this term is going to actually cancel a bit with that term, and then we'll end up with a basis function. So actually it ends up being quite simple. So we need the gradient of this link function, but it has this funny form. It's this is the sigmoid, which I've rewritten 1 plus e to the minus f to the minus 1. The gradient of that is computed. I can never remember. It's a variant of I don't even remember which rule. But basically, you end up with a 1 over the gradient of 1 over something is minus 2 over that times the gradient of the inside. It's just function of a function, really, isn't it? So it's the gradient of that, which gives you a minus 2 and a minus 1 in front. Have I missed the minus 1? Oh, no, but then there's another minus because of the fi, so that cancels. And then multiply by the gradient of what's inside the bracket, which is just e to the minus fi, yeah? So that's the gradient of this link function. And it's got this odd characteristic that it can be written in this sort of way. It can be written as 1 plus e to the minus f times e to the minus f over 1 plus e to the minus f. Now, it might not be 100% clear to you, but this thing here is just 1 minus g to the f. So let me just write down why that is. It sort of becomes very clear as you write it out. So e to the minus f over 1 plus e to the minus f. That is equal to 1. What am I trying to do? Minus 1 over 1 plus e to the minus f is what the claim is down there. The reason is because if I now multiply, I can turn this 1 into 1 plus e to the minus f over 1 plus e to the minus f minus 1 over 1 plus e to the minus f. Okay? And now that just gives me 1 plus e to the minus, oh, need another pen. So writing that out, that's quite simply 1 plus e to the minus f minus 1 over 1 plus e to the minus f. So that's just e to the minus f. Have I done that? Yeah. So that's true. Yeah. So that's e to the minus f over 1 plus e to the minus f. So that's the relationship between the two. Let me just clarify that bit. So this object here, since that itself is g of f, yeah, this is just 1 minus g of f. So this is g of f, and this is 1 minus g of f. So it's just this weird trick of writing down the derivative in terms of itself in the function. And the reason we do that is because it makes the gradients now look kind of quite nice. Because when we substitute that derivative in, that g of f, this is f in here, from here, this is g of f times 1 minus g of f, so that g of f cancels. Okay, and that leads to this really nice intuitive looking gradient. It's funny how often gradients look intuitive. That says that the gradient of the objective is yi, where that's your label, times 1 minus your prediction function. So if the class is labeled 1, and you're predicting 100% confidence that this data point is 1, like this becomes 1 minus 1. And so the whole thing's 0. But if you're 100% confident it is 0, so the largest thing this can be would be 1 minus 0. Like if you had no confidence that it was 1, then you would take a large step in the direction of your bases. If you go all the way back and look at your perceptron updates, you'll see the perceptron update is really similar to this. Only in the perceptron, of course, there's no... this is like a soft perceptron. In the perceptron, the output was a sort of like a hard thresholding. But the perceptron update actually looks really similar to this. And conversely, if you've got the label the other way around, so if your class is 0, then you get a large gradient if you're predicting high probability. So that's the sort of what the stochastic gradient descent updates will do. If you do any batch methods or whatever, you just need to sum over the entire gradient to get it out. Okay? So I think in the lab class, what I've asked you to do is, I think stochastic gradient descent using this implementation. So it's sort of, the model itself, you've seen the objective before, and then this is going to give you your learning rule. This is the sort of thing in early machine learning people would say is the learning rule, the update of the weights, but we just think of it in the way we're teaching the course as stochastic gradient descent. Yeah, so importantly, sorry, I should have mentioned this before. So optimization of the objective function, we can't solve this analytically. So what we did in the Gaussian regression case, once we got to this case, we set this to 0, and then we solved the equation and found out a value for w, yeah? And then you can show that w is a minima for the objective. Here we can't do that. There's no such solution. You can write down, you can manipulate this around, but you always end up with w's on both sides. So you get like w is equal to some function of w. So this is it's like, high order polynomials are hard to solve. Most functions are actually quite hard to solve. So the nice thing about the linear regression case is that that's a quadratic form. Quadratics are one of the things that are really, really easy to solve, right? In fact, one of our best known optimization methods is fit a quadratic locally and solve the quadratic. Does anyone know what that optimization method is called? You actually study, I think, at high school. You don't get taught it in quite that way. Newton's method? So Newton's method, actually, when you look at what Newton's method is doing, is it's fitting a quadratic. It needs the curvature. Okay, so what Newton's method does, this isn't something that I was particularly meaning to talk about in the class, but Newton's method is a method for obtaining roots of equations. So generally it's talked about in a form like this. But if you integrate the equation you're looking at, what you can see is that you can, instead of assuming you're finding a root is finding the zeros, you can see that another thing you can be seen to be doing is trying to find a minima or a maxima in the function by locally fitting a quadratic. So in Newton's method, you need the gradient and you need the second derivative. That's all you need to fit a quadratic locally. So you fit a quadratic, so let's say you're here, Newton's method tells you fit a quadratic here, then optimize the quadratic, so move there. That actually gets you here, and then you just do the same thing. And it's an iterative method, and then actually around here probably, as you get close to the minima, they often look very quadratic, so you move quickly to the minima. We're not really studying that in the course, but the same method works in high dimensions, and it's a very popular method for optimizing systems such as this, Newton's method. I think that's called, I think it relates to iterative reweighted least squares, I think, as an algorithm for fitting these things. There's lots of algorithms for fitting these things, as you can imagine. Because the right algorithm for fitting this sort of depends on various things. It depends on the size of your basis or your features. It depends on the number of data points you have. It depends on whether you just want a one-off solution. You can get numerical problems, all sorts. So you'll just look at stochastic gradient descent, but there's many, many ways of trying to minimize these things. So Newton's method or gradient-based optimization. So this is similar to the matrix factorization example you did. If you've got very large data, in the large data case, then you tend to use stochastic gradient descent, which is where you just take, instead of, so if you remember back to the early lectures, I think in the quadratic error surface, the one that we could actually minimize, how I tried to persuade you that linear algebra was worthwhile. We had an example, I think, where the error surface was like this. So it was actually a quadratic error surface. That's why we were able to solve it directly in the end. We were able to just go direct to the minimum with matrix linear algebra. But before we went direct to the minimum, we tried it in various different ways. We sort of looked at cases where you sort of did coordinate descent. So we optimized in that direction and that direction, and we saw that could be very slow. That was when we were optimizing M and C iteratively. We looked at gradient descent, where we just started and computed the gradient, which would be orthogonal to these contours, and then we found that actually could also be quite slow as well. Yeah. So in fact, it doesn't tend to do that. It tends to sort of oscillate either side of the minimum. I've drawn it incorrectly there. And then we looked at stochastic gradient descent, where instead of computing the whole gradient, as we have here, we just said, okay, well, I'll just take I'll just look at one data point and see what it thinks the gradient is. And it won't get the gradient right. So it might point in that direction. It might even point against the gradient. But you just keep doing it. It's so cheap to compute because, so the reason it's efficient is because to compute this batch gradient here, you have to do a sum over n. To do the stochastic gradient, you're just doing one of these. So it's 1/n of the cost. So each move is more stupid, but for very large data, it turns out that you head towards the solution in the end. Because for very large data, what happened, right? You spend an enormous amount of effort computing the gradient at this point. You compute like, you do a sum over 5 million data points to compute the gradient at that point, and then it goes, okay, there. But actually, you could have taken 1,000 of your data points, right, and just said, what do you think the gradient is? And they would have roughly pointed in that direction. So it's an estimate, because it's a law of large numbers thing, right? Now, the stochastic gradient descent is the extreme case of that estimate, where you just ask one data point, what do you think the gradient is? And then you make a move. So in that case, what we saw is we sort of bump around a little bit on our way to the minimum. Of course, and then after that, we solved it, bang, by just going straight to the minimum. Now, we can't do that in this case. We can't solve this system. So the closest thing to that would be Newton's method, which would be approximate the error surface. So our error surface wouldn't look quite quadratic. It would look like what would it look like? It looks like a product of these sigmoids. So it looks like it's sort of one way of thinking about it is in the weight space. The way the error surface looks is, so I'm trying to draw it from above. Every data point, so if this was a two-dimensional case, why did I draw a surface? I shouldn't have done that. Actually, every data point lands giving you a sigmoid. So this is a sigmoid sort of in this direction. So if I look down this way here, what I would see is something, actually I meant to have it the other way, something like that. Yeah? So each of these is sort of saying, oh, you know, and now this one's saying something like that. So this one's saying this space is invalid, this space is invalid. Every time you get something, you get some area where it says part of the space is invalid. In support vector world, this is called the version space. But we just think of this as the likelihood. So you end up with this sort of surface that is determined by all these sort of little hoods coming up like that. And then what you do is you could approximate it at any point with a quadratic, move to the minima, then reapproximate that with a quadratic, move to the minima. That would be Newton's method. So Newton's method doesn't make any sense in the linear regression case because it already is a quadratic. So that's, to be fair, that's beyond the scope of anything I'm going to ask you in the exam or anything. I'm just trying to give you an overview of, you know, the complexities of how you optimize in general, and, you know, give you the sense that even when you've got here, for a company like Facebook who do this, they do this every night to every one of you, actually. Who here's not on Facebook? Okay, they are doing it every night to every one of you. You are being represented by Facebook by a vector in this space. I'll talk about that a little bit. Oh, here it is. So it's actually interrent companies. That's a new form of... So actually, it's not just Facebook that is doing this to you. You are being treated as a vector by Facebook and everyone else. And what they're doing is they're using it for various things, like determining your ad ranking. They're using it for determining, your ad ranking, your feed ranking, like what your feed, what's presented to you, which friends' feeds are presented to you, what are the adverts on the side. I mean, actually, this is always a bit dangerous. I shouldn't call up Facebook because I have to cancel the video in case someone's written anything rude on my Facebook account. Oh yeah, and I have so that's a bit bad. I have ad block turned on, so we can't see the ads. How do I pause ad? Don't pause ad block. And then yeah, so now I've got adverts. So hey, it thinks that I'm a stylish guy. So this is okay. Let's drop that down. This is Michael Black, who's a colleague in Germany who likes making coffee. I like Michael. I like coffee. It's decided that that should come up high. These are the ads it's given me. Oh no, that's the trending. These are the sponsored links. So this is the one it's given me. It thinks I should be buying a men's jacket for $13.11. Well, actually, I don't know. It's doing that in some sneaky way because I am looking for bloody USB chargers. I would never buy a Nissan X-Trail. It's got that seriously wrong. That would be like the last car on earth I would buy. I mean, it's not only small and crummy, but it's like designed for people who really want a 4x4 like a Range Rover but can't afford one. It's like the worst car. Don't ever buy one of those. Look at the price, $21,000 to $32,000. My God, it's got that wrong. But you know, of course it's got it wrong because it's just what it's using is actually quite a complex feature set based on my behavior, probably on the internet and also various other things in order to predict what I'd be interested in. It's also having to combine the advertiser. So it's actually making a classification. It's combining me and an advertiser, and then it's making a classification as to whether we'll match or not. And it's got an enormous amount of data about this, right? So the way, what happens at Facebook is there are feature engineers who will be developing new variants of phi. So there are people whose job it is to say this is an interesting feature for advertising or for friend recommendations. Same thing is done for friend recommendations, you know. They live in the same town, they work in the same place, they have overlapping friends of this type. Those are all things that go into phi. But every night the learning is redone, and it's done using stochastic gradient descent to try and predict who's likely to click on what. Because if I click on that, how much money does Facebook make?
0.02 cents or something like that.
No, way more.
Really?
They'll make like, for these, so the top insurance ads on Google, how much would we make for Google if we search for car insurance? How much would Go Compare paying for that? If I click there now, how much money will Google make? Who thinks it's less than £1? Who thinks it's less? Well, so obviously the ones who think between £1 and £10. Yeah, and who thinks it's more than £10? Okay, so let's see if we can find the answer, because it is online somewhere. Car insurance. What's it called? I can't even remember the right things to search for. It's keyword bidding. Car insurance. 20 most expensive keywords in Google AdWords. Okay, so it's $54. Isn't that shocking? For one click. If you click on Go Compare, that's the order they're paying. I mean, so these ones, insurance is massive. So this teaches you one thing, right? The insurance industry is massively inefficient. If their main aspect, like that could be, for my insurance each year, that's about 20 to 25% of the cost. And it also makes you understand why they try and draw you in with low prices, and then they lock you in by upping the price. Loans, $44. Mortgage, $47. Attorney, so this would be particularly claims attorneys, $47. It's an extraordinary amount of money, isn't it? For that one click. Now, Facebook would be different. They've got a very different model, of course, because Facebook is more targeted in terms of the advertising. But we're talking dollars, or pounds. We're not talking 0.1 cents. The expected, of course, most people don't necessarily click when people do these searches. So the expected amount of money coming in is less, because basically I would just skip through all these AdWords personally. Well, that was the wrong one, wasn't it? It's car insurance. And I would then go and probably just take this one here. So if I click on this one, Google make no money, which is ironic, isn't it? Because there's their sponsored link there for $50. They're looking at, they make a prediction. Google make a prediction of what the probability I'm going to click on that is. They multiply that probability times the amount people have bid. And the way they do that is they look at, they understand things about me from my internet history and whatever else. They've got me logged in and everything else. And they use that information plus information about this ad in the same way Facebook are doing to decide which to present first. That gives them an expected amount of revenue from presenting the advert. These are ranked and presented according to that expected amount of revenue. How is the probability of me clicking computed? Logistic regression. It's as easy as that. Because it's super fast to do. Because in effect, they've got these feature sets for me, for you, for every one of us, are permanently computed and permanently associated with our account somewhere, so that when we do a search, all they have to do is compute the inner product W of whatever the feature, the combination set between us and their advertiser is, and then they can get this probability out by going through a sigmoid. That went through a sigmoid right there. So actually, they retrain that every night. Well, Facebook certainly do. I think I know the guy, Joaquin Quinero Candela, who's an ex-collaborator, used to be in charge for the ads ranking on Facebook. And so they've actually published how they're doing that. So their paper's here. So the cool thing about it is that they do, I used to work with, both Ralph and Joaquin, and Ralph's now at Amazon. He runs Amazon in Europe. And this is basically explains, broadly speaking, how they do it, which is decision trees to create. They actually have a very complex basis set. So they have decision trees as a sort of first filter as well. So they use decision trees and logistic regression. So phi is some result of a decision tree. We haven't talked about decision trees. Why have we not talked about decision trees? Not because they're not interesting. They're interesting and they're very cool. They just don't really fit in with the broad framework I've given you as probabilistic modeling. Yeah, everything you've seen you can think of as a probabilistic model. Decision trees are sort of slightly outside that framework, so it was hard. It would like taken probably 2 lectures or something. Well, it had taken a lecture, but we could have done it in a lecture, but I don't know. We've only got so much time. So that's all being done by logistic regression and decision trees. Decision trees are also very quick to compute, and that's being retrained every single night. It has to be all quick because the number of possible matches in terms of how many people are on Facebook, what order? Billions. How many advertisers? Millions. So if you want to, every time someone logs in theory, they have to check 1 million adverts to see if you're viable. So they have lots of heuristics for which adverts they check. But that's a load of other work as well. And the better they do this, think how much money this is transforming into. When you're thinking about the order of how much money they're making per click, getting this right, presenting the correct adverts that people actually click on, leads to astronomical changes in their revenue. I mean, this is the single most important thing pretty much those internet companies are doing, is training a logistic regression to improve the calibration. Why do you think they want you to be logged in to Google and everything else? It's all about understanding you better so that they can advertise to you better and make a lot of money. Okay, so just to finish on, because the world's not just about money. Health and wealth, 2 important things. So for health, I'd like to just give you a little overview. I just want you to see the principles. I don't expect you to remember the details of this. About how this framework then projects onto, say, something else, which is Poisson regression. So Poisson regression is not about counting binary things. It's like counting incidents, number of counts. So Poisson's a counting distribution. So if we look at the Poisson distribution, I won't be asking you about this in the exam, so don't worry about this form. But if we had a probability over y for non-negative integers, don't think that says negative, that's non-negative because it covers 0 as well. It's a distribution over all the non-negative integers, so 0 upwards. So it's a good distribution for goal scoring in football. Like, how many goals do you expect in a game? Well, if you look at the scoring rate, you can sample from this probability distribution that has this form. So lambda is a rate parameter, which is the scoring rate. So it turns out, like in Premiership football, most teams will score about an average of 1 goal or a little bit over 1 goal a game. A good team will maybe score up to 2. And if you sample from a Poisson, you see things that look like football scores, right? So you can watch a match and think it's very exciting, or you can just sample from a Poisson on your computer and have the same level of excitement. So Poisson distributions, I've got Ricardo Andrade Pacheco, a PhD student who's just graduated of mine, is in Uganda, and he's fitting Poisson distributions to disease data in Uganda as we speak, so across the whole country. So the country is split into districts, and he is doing exactly this type of modeling where he's trying to predict disease rate according to incoming information so that they can respond. There's rains coming in, cholera rates increase, so you can see what's going on there. And the way he does that is this rate parameter in the Poisson. So this is what the Poisson looks like. This is a Poisson with a rate of 1. So it's quite likely to have 0 counts. So if we had a Poisson rate, if the disease rate in this room, if we had a rate of disease in this room that was 1, then with greater than a third probability, no one would be diseased. Exactly the same probability, 1 person would be diseased. And then it goes down like that, right? So the probability of 10 people being diseased when there's a disease rate of 1, the probability of you all not turning up is 0, basically. Disease rate is 3, still approximately 0. Disease rate 10, now we start seeing this, and this is a fact that the variance of the distribution is, the standard deviation distribution changes as the number goes up, is known as dispersion. So it's a sort of well-known distribution for disease. So if we wanted to model disease over time, sort of like who was not going to turn up, if I wanted a model to see how many, so We know that because people would only not turn up if they're ill, that like 10 people must be ill today, right? So we know the disease rate isn't 1 because there's 10 people missing or something. Either that or they gave up the course. So we could model as a dropout rate or something like that. So what we do in this case is we use a link function that's a log. So the log rate is given by the generalized linear model, by the linear model. Now, what I've written here to make it explicit, this is where modeling gets interesting, is I've written one function which is a spatial function and one function that's a temporal function. So in Uganda, you've got different areas with different base rates of disease because some areas have a high with mosquitoes, there's a lot of malaria, or the altitude can affect these things, or you might have particular water features that mean cholera is high. That's a spatial effect, right? But then you have temporal effects because, you know, you get the rains coming in and disappearing. So you've got two effects, and you might be interested in separating these two effects, writing them separately, modeling them as two separate functions. So this is the sort of thing you do. You say the log rate of a Poisson is given by the addition of two separate functions. And this is known as a separable distribution. But when you write it in this link function, you have to be very careful. Are you saying that the effect of these two functions combining the spatial and temporal effects is additive? Is that what you're saying? You're thinking the answer must be no, or else he wouldn't say it in that leading way. No, it isn't. It looks additive. But, of course, the actual rate itself, that's the link function. It's called a log additive or a log linear model. But log additivity implies multiplication because the rate itself is the exponential of these two. So this is what we would use in machine learning. And this is, you will always hear people talk about log link functions in GLMs because machine learning people care less about saving lives and only making money or something, I don't know. But this is very much more a statistical thing, but it's the same thing, it's the same framework. So you'll hear log additivity, but be careful. This is the way we'd write it in machine learning. This is the transformation function, the exponential. So really it's a product model. Really it's two functions multiplied together. So be very, very careful with link functions because you think you're saying something additive, but in practice, the link function, the nonlinearity means you're saying something very different. So it's an attractive way to write down a model because you think, oh, look, I've got these additive components. No, you have multiplicative components. And that's a real trap. People get misled by that all the time when they're doing these generalized linear models. Okay, so that's it for today. Well, not it for today, because of the lab class, where you'll just do some logistic regression. They normally are outside, we're a little bit over, but if there's a quick question on that, I'll take it now. Okay. Right, see you in an hour's time.